Today we'll be doing the integral from 0 to infinity of the natural log of x plus 1 times the natural log of x divided by x times x plus 1 dx. And we will start off with a substitution. So we're going to let x plus 1 equal 1 over y. But that means that y equals 1 over x plus 1, and that x is 1 over y minus 1, and finding the bounds of integration, y1 is going to be 1, and y2, it's going to be 1 over infinity, but that's approaching 0. And dx will be negative 1 divided by y squared dy. So our integral is now going to be the integral from 1 to 0 of the natural log of 1 over y, then the natural log of 1 over y minus 1 divided by 1 over y minus 1 times x plus 1, which is 1 over y, and dx is minus 1 divided by y squared dy. And we could use this negative to flip the bounds of integration. And rearranging some things, we have the integral from 0 to 1 of y natural log of 1 over y, and then the natural log of 1 over y minus 1, 1 over y minus 1, and then times 1 over y squared dy. And one of these y's will end up canceling, and we can distribute the y here. And we're going to end up with a integral from 0 to 1 natural log of 1 over y times the natural log of 1 over y minus 1 divided by 1 minus y dy. We could further rewrite this as the integral from 0 to 1. The natural log of 1 over y is the same thing as the negative the natural log of y. And then we're going to have the natural log of 1 minus y divided by y, and then divided by 1 minus y dy. We could use logarithm rules for this term. So we have the integral from 0 to 1 of negative the natural log of y, and then the natural log of 1 minus y minus the natural log of y divided by 1 minus y dy. And distributing that, we have the integral from 0 to 1 of negative the natural log of y, the natural log of 1 minus y, and then we're going to have plus the squared logarithm of y, all divided by 1 minus y. We could split them, dy. So we now have the integral from 0 to 1 negative the natural log of y times the natural log of 1 minus y divided by 1 minus y dy, and then plus the integral from 0 to 1 squared logarithm of y divided by 1 minus y dy. And from here we'll do this second integral first. So we have the integral from 0 to 1 squared logarithm of y divided by 1 minus y dy. And from here we'll use geometric series. So we know 1 over 1 minus y is the sum from 0 to infinity of y to the k. So we're going to have the integral from 0 to 1 squared logarithm of y, and then the sum from 0 to infinity y to the k dy. And then swapping the sum and integral, we have the sum from 0 to infinity, and then the integral from 0 to 1 of y to the k squared logarithm of y dy dy, and we'll make a substitution. So we're going to let z equal the natural log of y, but that means that e to the z is equal to y. z1 will be negative infinity, and z2 will be 0. And dy will be e to the z dz. So we have the sum from 0 to infinity, and then the integral from minus infinity to 0 of e to the z to the k power z squared. And we have dy is e to the z dz. So we have the sum from 0 to infinity of the integral from negative infinity to 0 of z squared, and we're going to have a e to the zk plus z power dz. And we're going to make one last substitution for this integral. So we're going to let r equal zk plus z, which is actually no, negative r. So that means that r is negative zk minus z, which is z times negative k minus 1. And for the bounds of integration, r1 will be positive infinity and r2 will be 0. And solving for z, we have z is r divided by negative k minus 1. But that means that dz is 1 over negative k minus 1 dr. So we're going to have the sum from 0 to infinity, and the integral from infinity to 0 of r divided by negative k minus 1 all squared. We have e to the negative r dz is 1 divided by negative k minus 1 dr. So we have the sum from 0 to infinity r squared. It's going from infinity to 0, and this could be written as negative k plus 1, the whole thing squared, e to the minus r, and then 1 over negative k plus 1 dr. But we can use this negative to reverse the order of integration. So we have the sum from 0 to infinity, and the integral from 0 to infinity of r squared divided by k plus 1 squared. And then we have e to the minus r divided by k plus 1 dr. So this is equal to the sum from 0 to infinity 1 over k plus 1 quantity cubed, and then the integral from 0 to infinity of r squared times e to the negative r dr. But this integral is just the gamma function evaluated at 3, which is equal to 2. So now we're left with twice the sum from 0 to infinity of 1 divided by k plus 1 quantity cubed. And making a change of index, we have twice the sum from 1 to infinity of 1 over k cubed, but we recognize this as twice the zeta function at 3. So picking up where we left off, we have twice the zeta function at 3, and then minus the integral from 0 to 1 of the natural log of y times the natural log of 1 minus y all over 1 minus y dy. And we're going to make one last substitution. So we're going to let 1 minus y equal s, but that means that negative y equals s minus 1. So y is going to be equal to 1 minus s. So that means that dy is negative ds. And the bounds of integration, s1 will be 1 and s2 will be 0. So we have, for the first integral technically, so we're going to have minus the integral from 1 to 0 of the natural log of 1 minus s, the natural log of s divided by s, and we have negative ds. I may use one of these negatives to flip the bounds of integration and keep this extra negative sign. So we're going to have negative the integral from 0 to 1, and then we have the natural log of s times the natural log of 1 minus s divided by s ds. And from here we'll use the series expansion for the natural log of 1 minus s. So the natural log of 1 minus s will be negative the sum from 1 to infinity s to the k power divided by k. So replacing that into the integrand, we have negative the integral from 0 to 1, the natural log of s divided by s, and then the sum, negative the sum from 1 to infinity, s to the k over k ds. These negatives end up canceling, and reversing the sum and integral, we have the sum from 1 to infinity, 1 over k, and then the integral from 0 to 1 of the natural log of s, and s to the k power divided by s will be s to the k minus 1 ds. So from here we'll use integration by parts. So we're going to let u equal the natural log of s, which means that du is 1 over s, dv is s to the k minus 1. So integrating that, we have v is s to the k over k. So we have the sum from 1 to infinity, 1 over k, and then we're going to have the natural log of s times s to the k over k from 0 to 1, and minus the integral from 0 to 1 of s to the k over k times 1 over s ds. And this limit ends up being 0. So we're going to have negative the sum from 1 to infinity. We're going to have a 1 over k squared term, and then the integral from 0 to 1 of s to the k minus 1 ds. So we have minus the sum from 1 to infinity, 1 over k squared, and evaluating that integral, we're going to have s to the k over k from 0 to 1. So evaluating that, we have minus the sum from 1 to infinity, 1 over k squared times 1 over k, which simplifies into minus the sum from 1 to infinity of 1 over k cubed. And this sum is just negative the zeta function at 3. So putting everything together, our goal integral is twice the zeta function at 3, and then minus the zeta function at 3, which is equal to just the zeta function evaluated at 3. So that is the final result. Thank you very much for watching.